Now I want to start again from the tetrahedron here, and I want to change slightly the notation, and then I want to make some generalizations. In particular, let's use the following notation. For example, this side here is described by this vector e1, then this other side is described by the vector e2, and then I have e3, which is this side here, e3, in these directions. And for example, the mode of e3 is equal to the length of this edge, this side here, and so on for e2 and e1. Then I can define this arrow, this red arrow here, to be L1, and then I can define this arrow here, this red arrow, to be L2. Then I have L3 here and L4 here. Now there are some simple formulas for L1, L2, L3 in terms of E1, E2, E3. In particular, L1 will be proportional to the cross product between E2 and E3, and in particular we simply normalize L1 in such a way that its mode is equal to the area of this face of the tetrahedron. So I multiply by 1/2, and then I have E2 cross E3, and similarly we have L2 equal to 1/2 E3 cross E1, and then I have L3, which is equal to 1/2 E1 cross E2. Now with the simple calculation it is possible to show that L4 is equal to minus the sum of L1 plus L2 plus L3, and this can be done quite easily if, for example, you express this vector here, for example, this vector, you can express it as the difference between E1 and E2, and similarly you can express this vector here as the difference between E3 and E2. And by doing the calculation you can show this simple formula. So L4 is described by L1, L2 and L3, so it depends on them, and therefore we can just take L1, L2, L3 to describe the areas of this tetrahedron. And in particular, it is also possible to use L1, L2, L3 to describe the volume, but in this case I'm not going to describe the volume, I'm just going to be interested in describing the area of the faces. So the mode of L1 will be the area of this face, and so on, as I said. Now it is possible to rewrite these three equations more compactly in the following fashion. So we have the vector LA in general, and this is equal to 1/2. Then I have the Levi-Civita symbol epsilon A, B, C, EB cross EC, and the indices A, B, and C can take the values 1, 2, and 3. And you can check that this vector equation contains those three up there. Now at this point we can go to index notation. So the vector LA, you can see that this is a vector of vectors if you want, because this index A goes from 1 to 3. So we have three different vectors because A can take three values. And now we can also write this arrow with index notation. So I put I here to denote the fact that, due to the fact that here we have this arrow, we have three components, and I'm going to label the components over there with the letter I. And we can rewrite this as 1/2. Now I still have epsilon ABC. I have another Levi-Civita symbol because here I have this cross product, and then I have the components of EB and EC. So I can write epsilon IJK EJB EKC, like this. These elements here are also known as the triads, and this vector or these components LIA can also be rewritten in terms of what we previously called the densitized triad EIA. You can see that I have simply switched these these two indices. I will become a subscript, whereas A will become a superscript. So here I simply have to rewrite the same formula, but I have 1/2 epsilon. This A will become a superscript, so I have A, B, C. And then I have epsilon I. This I will become a subscript, JK, EJB, EKC. So this is the classical expression of the densitized triad. Why is it classical? Well, because we are reasoning in terms of classical quantities. In this case, we have not quantized anything. We are considering simply a tetrahedron, and there is nothing quantum here at this point. And in particular, now we can also define the flux across a surface in the following fashion. So we have an integral of EAI and A, so this is the normal. These are the components of the normal to the surface, and then I need to integrate over two parameters, lambda1 and lambda2, which describe the surface. The surface is parameterized by two variables because it is two-dimensional, so we are reasoning with two-dimensional surfaces. Now we can simply define this to be EI, which is just EI, A, and A. And let's rewrite EI in a different manner. So EI is equal to EIA and A, and by using the definition for EIA that we have written above, we can rewrite this as 1/2 epsilon I JK, epsilon ABC, EJB, EKC, and then I can rewrite NA, the normal to the surface, by taking a cross product. So I have the Levi-Civita symbol EA dE, and then I have the derivative of XD with respect to lambda 1. You can think of XD as the vector X, which spans the surface. As we move along the surface, we are varying the parameters lambda 1 and lambda 2. So X is a function of lambda 1 and lambda 2. And then here I have dxe, which is the second index here, with respect to lambda 2. Now we can multiply this Levi-Civita symbol with this Levi-Civita symbol here. You can see that the repeated index A, there is a formula for epsilon ABC and epsilon ADE. It's quite a simple formula. I will show you in a moment. I have 1/2 epsilon IJK EJB EKC. And then here I have a product of Kronecker deltas, delta B D, delta CE, and then I also have a subtraction of a product of Kronecker deltas, delta BE, delta CD, and then I still have dxd, d lambda 1, dxe, d lambda 2, like this. And now we can do some simple manipulations. In particular, I can write 1/2 epsilon IJK, EJB, EKC, DXB, D lambda 1, DXC, D lambda 2, minus DXC, D lambda 1, DXB, D lambda 2, which is equal to epsilon IJK. Now if you play with the dummy indices there, you can see that this 1/2 will be cancelled because these two terms will sum. So here you see a minus, but if you play with the dummy indices, you can change this to a plus, and what you get is something like this: EJB DXB D lambda 1, and then I have EKC DXC d lambda 2, and this is equal to, now you can see that basically this is the derivative of the position vector with respect to lambda 1, and then you take the cross product with the same position vector, I mean the derivative of the same position vector with respect to lambda 2. So what we have shown is that EI, the vector EI, can be written like this, and therefore EI can be written as the mode of dx d lambda 1 cross dx d lambda 2 squared. And if you remember, when you integrate the mode of dx d lambda 1 cross dx d lambda 2, and then you integrate over the two parameters that describe the surface, d lambda 1, d lambda 2, you get exactly the surface. So this comes from multivariable calculus, and basically this means that you can rewrite the surface as the integral of the square root of ei d lambda 1 d lambda 2, which is something that we have already seen in the previous video, where ei was quantized, and we saw that ei under the square root plays the role of the area operator. So we have the area operator. Now at this point in the classical case, we can see that indeed this describes a generic surface. So we started from a tetrahedron there, but by taking an integral here, we were actually generalizing the theory, because here we are integrating over a generic surface, and this holds for every kind of shape. So this is not only true for tetrahedra,